Hello. Today we're going to talk about similarity as it applies to solids. And it's really very, very simple. It's exactly the same as it was with the polygons and two-dimensional figures. For instance, if we look at, say, 3 pyramids, this pyramid and this pyramid, these are square pyramids, of course. These are similar. This one is just expanded in every direction by, it's about 33%. So, in other words, I multiply this one by about 4/3 to get this. So if this had length 3, this would have length 4. This had height 3, this would have height 4. This over here, this is not similar. This is just squished up along the horizontal axis here, but it's not really similar. It's not expanded in every direction or contracted in every direction. For instance, if we started with this one here in the middle, we could say that this was a contraction, a scale factor less than 1. Or if we go this way, it's a scale factor greater than 1. Exactly the same as what we did in 2 dimensions. Aside from polyhedra, we can use cylinders and spheres also and produce similar solids from them. For instance, with the cylinder, we have to expand the radius and the height by exactly the same amount. That would be the scale factor K. With a sphere, all we have to do is change R. And in fact, just like with circles, all spheres are similar to all other spheres. There's no way around that. You see a sphere, it's going to be similar to another sphere. The reason would be that spheres, like circles, only have one parameter. So 2 different radii can always be written as R1 equals K times R2. You can always do that. If you don't like that, if it doesn't seem reasonable to you, just write K equals R1 over R2. You can always find some number which will act as a scale factor, shifting one number to another one, if there's only one number to worry about. Most of the time we have at least 2. Cubed would be another 3-dimensional object, which are always congruent, always similar to each other, because there's only one parameter, the side S. If you change that, you change everything. And if you're going to produce another cube, you have to change that. So it works just like this does. And previously we saw squares were also similar to each other. All squares are similar because, again, there's only one parameter. Maybe I should have mentioned at the beginning, I don't think most of the state exams, or maybe I should say I do think most of the state exams don't have similarity as it applies to solids as questions on their exam. I don't think they cover that, but maybe some do. Last time I looked, similarity as it applies to solids, it wasn't in most of them, but I think it might be in some, so I went ahead and threw this in. You may not even need this section. You can check with your instructor. Learning it won't hurt you any, but if you just want to tailor your studies to exactly what you need to do well on the state exam, check with your instructor. I'm pretty sure you can skip this one. What's the important part about all this anyway? Why are we even talking about similarities that applies to solids? Well, the most important thing is that if we have a scale factor between the 2 solids, all the linear factors will change as the scale factor. For instance, in the pyramid, we had the height, we had the side lengths, and we had the slant height. Those are all linear measurements, and they will all get multiplied by K. What about the square measurements, like, say, the base of the cylinder, or the lateral surface, or the entire surface of the cylinder, or the surface of the sphere. What happens to those things when we use a scale factor of k to produce a similar solid? Well, we square it. For all the squared measurements, we square the scale factor. And that'll give us the ratio of, for instance, the base in this cylinder and the base in this cylinder. B1 over B2, say. We'll call this B1 and B2. Well, the ratio of that, let's say k is greater than 1, so we'll put the large one on top. That's k squared. And as you remember from the two-dimensional version, the area of polygons and circles also moved as the square of the scale factor. So the area of two similar rectangles, say with a scale factor of k, the areas had a scale factor of k squared. Well, guess what happens with volume? Put B2, we'll say that's volume for this cylinder, let's say it's V2. And this one is V1. Well, V2 over V1, guess what? It's k cubed. And this was probably the most important part of this section. There's really not a whole lot to say about these that we haven't already said in the two-dimensional case. This is the only thing that's any different. And it makes sense. We've got volume is always something cubed. It's always in cubic units. And our scale factor is cubed. That is the ratio of the two volumes of the two similar solids. That ratio is k squared, where k is the original scale factor. Let's say it's really very easy. So let's prove it. Let's work some problems and see how easy this is. Which dimensions would correspond to a similar triangular prism? Similar to this one here. That looks better. So all we need to do is figure out which of these sets of three numbers correspond to multiples of all three numbers, and they have to all be the same multiple. For instance, check the largest of these, because that doesn't change. After all, if we multiply this by some number, and it has to be the same number, k, it'll be k times 10, k times 6, k times 4. Well, k times 10 is still going to be greater, assuming k is positive, and we're not dealing with negative scales. So if k is greater than 0, then k times 10 is still going to be greater than k times 6, and k times 6 will be greater than k times 4. That may not be useful, may not sound useful, but what it does is it tells you which ones to check first. In other words, say over here, the largest one would have to be the multiple of 10, the smallest one would be the multiple of 4, and they have to all be the same multiple. So, if this is 5, that means we multiplied by 1/2 to get 10. And the bottom one, the smallest one, that's 1, we should have also multiplied 4 by 1/2. No. 1/2 of 4 is definitely not 1. 1/2 of 6 is not 2. So we can scratch this one out. No good. Well, what about this? Again, check 10 against the biggest one. Well, let's see here. To get 8, we multiply by 10 by 8 over 10, right? Multiply that by 10, and we get 8. So 8 over 10 would be our scale factor to go from 10 to 8. What about the smallest one here, 2? Well, to get from 4 to 2, our scale factor would be 1/2. Well, that's not equal to 8/10. It has to be the same for all of them, so that's no good. Check this one. This is the biggest one. That corresponds to the largest one over here. That uses a scale factor of 2 to get from here to here. What about the smallest one? That's 6. So 2 times 4 would be 8. Well, that's no good, because 8's not 6. You can tell I've been to school. I know that 8 is not 6. So that's no good. Well, we got one left. Let's make sure we did this right and see if this one actually makes sense. What would our scale factor be to get from 10 to 25? 2.5? 2.5? Okay. So our smallest one here is 10. That should also be 2.5 times 4. And 2.5 times 4 is 10. Okay. What about 2.5 times 6? Well, that's 15. All right. Got it. All you had to do was figure out which of these can be turned into one of these 3 sets of numbers by multiplying every single number by the same scale factor. You can't multiply 10 by one number and then 4 by something else. That's contrary to the definition of similarity. Other than that, you can see this was a pretty easy problem. Well, here's another one of those oops problems. Let's see what we got wrong. The scale factor is 1 to 4. Okay. The volume of the smaller solid is 500 pi. Describe and correct the error. And let's see, that's the same as the scale factor squared. Uh-oh. But for volume, the scale factor is supposed to be cubed. And 1/4 squared does not equal 1/4 cubed. If the scale factor was 1, by the way, if it's 1 to 1, then it doesn't matter whether you're talking about linear measurements, area, or volume, because 1 squared, 1 cubed are all just equal to 1. But that's not the case here. So we should have written that 500 over pi, 500 pi over v sub v equals 1 over 4 cubed. I think that's 64, isn't it? 4 times 4 is 16, times 4 is 64. And if we set it up this way, the volume of the unknown volume is very easy to find. 64 times 500 pi. So you can see that any changes you make to the original solid produce really big changes in the volume, because you cube whatever you do. If you double the volume, if you double one of the linear factors, then you multiply the volume by 8. That seems like a big number to me. Or suppose you triple it, then you've increased it by 27. Another big number, I would say. Okay, here's one. You can consider it in 2 steps, or put the 2 steps together depending on how you like to look at things. What we have is 2 similar cones with the volumes of 8 pi and 27 pi. So the volume ratio, let's say V1 over V2, that's 8 pi over 27 pi. Cancel the pi's and you just get 8 over 27. That's for the volume. But remember, the scale factor for volumes is going to be k cubed, given an initial scale factor for the 2 similar solids, in this case cones. If the scale factor is k, then the ratio for the volumes is k cubed. And what we have here is that k cubed equals 8 over 27. So I think that would give us that k is equal to the cube root of 8 over the cube root of 27. And that's 2 over 3. 3 cubed is 27. 2 cubed is 8. Well, that's our scale factor. But they asked us, what's the ratio of the lateral areas of the cones? And it wouldn't matter if they'd said the surface area of the cones or the base area of the cones. These are all squared parameters. So their ratio, we'll say A sub L, lateral area of cone 1, and A sub L2 for the lateral area of cone 2. Well, that's going to be the square. That's going to be k squared, or 4 over 9. And I think we have that right here. The answer would be C. What you had to remember was, given the ratio of the volumes, you take the cube root, that'll give you the scale factor, and then you square that. Or, if you're familiar with this notation, depending on what they showed you in Algebra 1, if you take something like the cube root of x and square it, well, you can rewrite the cube root of x as x to the 1/3. And you square that, and you get x to the 2/3, which is the cube root squared. It's exactly what you're looking for here. So what we could have done is taken v1 over v2. Let's see if I write it down here. v1 over v2. Take the cube root and square it. So it's v1 over v2 to the 2/3. And if you punch that into your calculator, you should get 4 over 9. Here's one where they're going to ask us, I think, for a bunch of ratios. Yeah, they want to find the ratio of all these different quantities. Really, all you need to do, this is the trick, keep track of whether these quantities are linear, squared, or cubed, because the ratios will move exactly the same way. In other words, find your first linear scale factor if you can. Well, you always can. If you find one of the other ones, take the square root or the cube root, and you've got your linear scale factor. In this case, the whole thing is 10, and this top part is 8. So I think we can instantly write that our scale factor is 8 over 10, or 4/5. That's k. Starting with that, we can probably get all the rest of these just from this here. Let's check it out. The area of the top shaded circle to the bottom. Okay, that's this one to this one. Well, that's going to be k squared. That's 4/5 squared, or 16 over 25. Okay. The slant height. Well, that's a linear measurement, isn't it? Then it's the same as, it's just our scale factor. Pardon me, I wasn't applauding. A mosquito tried to come at me. If you're wondering, he's gone. Now, the lateral area of the top part of the cone to the lateral area of the whole cone. Say that again. The lateral area of the top part of the cone, that would be this here. This part excluding, would be basically the surface area of the cone excluding the base. And the other one is the lateral area of the entire cone. Well, once again, this is an area. That's a squared quantity. So we're going to square our scale factor of 4/5, and we already know that's 16/25. Now the volume of the top part of the cone to the volume of the whole cone. Once again, volume is a cube quantity, so we cube our scale factor. Well, 4/5 cubed, that's 4 cubed is 64, right? 5 cubed or 5 squared is 25, times 5 is 125. So there's our scale factor for the volume, 64/125. And the volume of the top part of the cone to the volume of the bottom part. Well, if the ratio is 64 to 125, or you could say 64/125 is the whole. Well, I'm not explaining that very well, am I? The ratio of the top part to the whole is 64/125. That's the whole thing versus this small one here. Well, if this one is 64, what's left over? This part that's left over here, whatever it is, and whatever equation we might have for computing the volume of a sliced cone, we don't really need any of that. If we just think of the whole thing as 125, this top part is 64 out of the 125, so what's left over is 61/125. So what we get is 64/125 over 61/125. We invert and multiply. The 125s cancel, and we get 64/61. This was the only odd one that they asked us for. The others, you just take powers of k, either square k, cube k, or k to the first power. Leave it alone. This one was a little bit weird. You just have to recognize that since we're using scales and ratios, 64/125 is this part. Think of 125 as the whole. Do your subtraction, get 61, and that's what's left over. Now this problem has several steps to it, and initially they ask us to find the volume of each unpeeled orange, and then compare the ratios, and then find the diameters, and etc., etc. I think there might be a different way to work this problem. The main thing about this is to get the ratios of the two volumes. That's, I think, the whole point of this problem. And we can do that without actually finding the two volumes. After all, we've got the volume for one is 4/3 pi 3.2 cubed. And over here on the bottom, what do we have? Almost the same thing, 4/3 pi over times 4 cubed. Well, everything cancels except this part, and we get 3.2 over 4 cubed. So now, anything else we want to do, we can instantly write our scale factor. After all, this is the ratio of the two volumes. The scale factor would have to be the cube root of that, or look at it another way, if the scale factor is k, then this is k cubed, because this is the scale factor for the volume. Well, that means that k is the cube root of 3.2 over 4 cubed. Makes it real easy to just directly write down the scale factor. Compare the ratios of the diameters to the ratios of the volumes. Well, this would be it, 3.2 to 4, because diameters, that's a linear measurement. All the linear measurements move right along with the scale factor. You could call this the linear scale factor if you like. So 3.2 to 4. That's the answer for the ratio of the diameters. Next thing they ask us to do is find the diameter of each orange after it's been peeled. The thickness of the peel is 1/8 inch, so we just have to subtract 1/8 from 3.2 and 1/8 from 4. And 1/8 is the same as 0.125. If we perform that subtraction, we get the diameter for orange 1, the smaller one, is 3.075. And diameter for the larger one would be 3.875. That's the ratio of the two diameters after we've peeled them. Remember, subtracting 1/8 from each one is not going to maintain the same ratio. You multiply the top and the bottom by the same thing, and you maintain the same fraction. If you subtract the same number from the numerator and the denominator of a fraction, you don't end up with the same fraction. In other words, think of 2 over 3. Subtract 1 from the top and the bottom, you get 1 over 2. 2 over 3 and 1 over 2. Definitely not equal. And once again, the ratio of the surface areas, that's just k prime squared, or 3.075, 3.875 quantity squared. And of course, the volumes, well, once again, all you have to do is take k prime cubed. So, in a sense, you could say that if you take the ratios of the diameters, multiply it by the ratio of the areas, you will get the ratio of the volumes, because k prime times k prime squared is k prime cubed, and it would just be this stuff cubed. I'm not sure what their point was here. Just reiterating the fact that areas move as the square of the scale factor, and volumes move as the cube of the scale factor, remembering that the scale factor always refers to the linear measurements. And once again, this is actually pretty easy. We're just going to apply scale factors to three-dimensional objects now. Before, we just used them with two-dimensional objects. We have a scale factor of 1 to 18. So the model has length 8 inches. What is the length of the actual car? Well, I think it would be 18 times 8, wouldn't it? Because 1 to 18 means that the actual car is 18 times as large. Or all the linear measurements in this model have to be multiplied by 18 to arrive at the linear measurements for the original vehicle. So how does that work? Let's see, 8 times 18. So the length of the car is 144 inches. And with 12 inches in a foot, that's actually 12 feet, which is a pretty small car, I think. I'm pretty sure a standard car is closer to 20 feet long. Oh well. It doesn't look like a very big car, does it? Each tire of the model has a surface area of 12.1 square inches. What is the surface area of each tire of the car? Well, remember that this is K. Then for area, we need K squared. Well, K squared is 1 to 324, which means that if the model has a surface area of 12.1, the surface of the actual car would have to be 324 times that. Well, I mean the surface of the tire on the actual car. So we just need 324 times 12.1. So in B, and I get 3,920.4 square inches for the surface area of the actual tire on the car. And lastly, for part C, they asked us to find the volume of the model car's engine given the actual car. Well, first thing we have to do is find K cubed. And for K cubed I get, wow, 5,832. That's our scale factor for the volume. In other words, the volume of the actual car engine is, or you could say car, is 5,832 times the volume of the model car. Well, let's see here. They give us the actual one first. So all we have to do is divide. In other words, we could write it this way. The ratio of our volume of the model car to the volume of the actual car is 1 over 5,832. Or we do some rearranging and get the volume of the model car is the volume of the actual car divided by 5,832. Now if you punch this into your calculator and divide it by K cubed, you get 1.5. And that would be inches squared. Not very big. That's why they call it a model, I guess. Again, actually a very simple problem. All you had to do was keep track of what your scale factors mean with respect to three-dimensional objects. There are two ways to do this problem here. First thing we could do is, since we're given the weight of the smaller ball, we could compute the volume and divide 1.2 by that volume and get kilograms per cubic centimeter. That would be called the density. Once we have the density, we can compute the volume of this one, multiply by the density and get the weight, and then the volume of this, multiply by the density and get the weight. However, this is a section on similar solids and scale factors. Remember, we're going to treat these balls as spheres. All spheres are similar to all other spheres. So all we need is a scale factor, and that'll apply to our 1.2 kilograms. In other words, for instance, let's say we went from 25 centimeters to 50 centimeters, meaning that we doubled the diameter. We would multiply the volume by 8. That means we would multiply the weight by 8 also, because the weight is related to the volume, not the surface, not the linear measurements. The weight depends on the volume. Normally it's written in density. In this case it would be kilograms per cubic centimeter. But we're not going to actually find the density. We're going to do it in a way that's probably a little quicker, easier, and more cleverer. Let's check out the scale factor from the small one to the middle one. And what do we get? 25 over 35. Well, that's the same as 5 over 7, right? And, okay, that equals k. But, we don't want k, do we? We want k cubed. Isn't that right? If k is how the diameters move, and those are the linear measurements, and we want to know how our cubic measurements move. That's volume. So we get 5 over 7 cubed. So if we work this all out, 5 over 7 cubed equals 1.2 over the weight of the middle snowball. That's the 35 centimeter one. In fact, that's how we got it. 5 over 7. It's 25 over 35. Well, we rearrange this and get the weight of the middle ball is 1.2 times 7 over 5 cubed. 7 over 5 cubed is about 2.744, and we end up with 3.3 kilograms for the middle ball. Okay, what about the large one? Well, we get k is 5 over 9, right? 25 over 45. Maybe I should have called this k1. We'll call this k2. So if we do exactly the same thing one more time, we get that the second scale factor going from the smallest snowball to the largest snowball is 5 over 9. We have to cube that to get our volume ratio, and then perform a little algebra, just like we did before, and get that 9 over 5 cubed times 1.2 would be the total weight of the large ball. It's like we did over here. We start with this equation, except that it's 5 over 9 cubed is equal to this stuff. This would be W sub L. Exactly the same algebraic rearrangement, and we get pretty much exactly the same equation with our K2. It's actually 1 over K2 cubed. That's how we rearranged it to get 6.99, which is pretty much 7, right? So if we take 7 and 3.3, we get 10.3. Let me try that. That was that way. Oops. That's 10.3. And then we add 1.2 and get 11.5. I think that's what they asked for, right? Yeah, the total weight of the snow used to make the snow figure. So this was, again, just a matter of using your scale factors and keeping track of linear factor versus the cube ratio. Again, pretty easy. Now here's one that's kind of, it's kind of interesting. We're going to have to use our head to do this one, because they didn't give us much to work with. They gave us a height from here to here. That's 12 feet. That's about all we know. Well, they also tell us that this plane separates this pyramid into equal volumes, which means that this whole pyramid has exactly double the volume of this top part here. In other words, the top part plus the lower part equaled the whole, and they break the whole up into 50-50, then if we count this as 1 unit, then the whole thing would be 2 units. Another way to look at it is the volume of the whole, the ratio of the volume of the whole to the volume of the top part is 2. So if I list this as base 1 and this as base 2, then the height corresponding to base 2 would be h2, and that's 12. The height corresponding to b1, well, we don't know what that is yet, do we? In fact, that's what we're supposed to be looking for. Well, we got a whole bunch of variables here, and we don't know what they are. But first thing we can do is simplify this expression. This is the formula for this top pyramid, and this is the formula for the volume of the entire pyramid, and that'd be 1 to 2. Remember, the whole pyramid is exactly double this top one. Well, we can replace h2 with 12, and we can write this as b1 over b2 times 1 over 12 equals 1/2. But wait a minute. We know what the ratio of b1 to b2 is, don't we? Because we know that this big one, this large pyramid, has double the volume of the smaller pyramid. So our scale factor for the volumes is 1 to 2. Our scale factor for the bases must be the cube root of that squared. In other words, put it over here. b1 over b2. We don't know b1 or b2, but we know their ratio. We know it has to be 1 over 2. We need the cube root of that, and then squared. The cube root of that will give us the actual scale factor, and then we square it to get the scale factor of the two bases, which are areas. Okay. So we could rewrite this as 1/2 to the 2/3. And this is supposed to be h1 over 12. Pardon me. Big mistake. h1 over 12 there. Times h1 over 12. And that's all equal to 1/2. So, now we can, matter of fact, let's do this differently. So by making use of the fact that we know this ratio, we can end up, after rearranging this equation, where we have 1/2 to the 2/3 times h1 over 12 equals 1/2. Do a little rearranging here and get that h1 is equal to 12 over 2, multiply through by 12, multiply, or divide through by 1/2 to the 2/3, which is just 2 to the 2/3. Remember, this is the shorthand way of writing this number, the cube root of this number, squared. In this case, it would be the cube root of 1/2, and then we square that cube root. We get all this stuff here. And this, of course, 12 over 2 is just 6 times 2 to the 2/3, which is about, I forget, 1.5 something. And you end up with 9.52 for the height of this large one here. The important part here was, number one, recognizing that your volume ratio is the cube of your scale factor. It's not going to be your scale factor, it's the cube. You have to take this, take the cube root, and then square it, and that gives you the scale factor for the bases. Then make use of the fact that we have b1 over b2, and even though we don't know either of these, we do know their ratio. So we can just pull out the b1 over b2 and rewrite it as 1/2 to the 2/3, as what we have over here. Once we do that, everything drops out and we get 9.52. The hardest part, I think, of this problem was probably recognizing that you've got all these variables here. One of them you have an actual number for. The others just look like a big mess until you recognize that you can actually replace b1 over b2 with a number. We can't replace b1 or b2 individually, but since we have the ratio, we do know the ratio. And that is the scale factor squared. Well, see, similar solids aren't really very difficult. And that's about it.